Hello, this is Jennifer Martinez, and in this video we're going to go over matrix equations. But before we define what a matrix equation is, let's go over the following definition of what a product of a matrix A is and a vector X. So it says here in the definition that matrix A is an n by n matrix, and it has columns A1 through AN. So here is A right there. X is an Rn, so there's n entries. By the way, each AI, we have an n by n matrix, so each AI has to have m entries. Each AI is an Rm. Then the product of A times X, denoted by AX, is a linear combination of the columns of A using the corresponding entries in X as weights. So the definition of this product is going to be X1 times A1, X2 times A2, all the way down through added to xn times an. For this to work, you have to have the right dimensions, the correct dimensions. So again, M is a m by n matrix. This one column matrix is n rows by 1. These two inner columns have to be the same. And the result is going to be an m by 1 matrix. So it's going to be m rows, and that makes sense because each column here, there's m of them, we'll see this down below, by 1. Right? So if you put this in matrix form, it would look like that. So if we multiply this A times this X in example 1, we're going to get this X1, which is a 4, times the first column, plus the X2, which is a 3 times the second column, and then plus 7 times the third column. You're going to get a linear combination here. Again, this X1 is the 4, X2 is the 3, and X3 is the 7. And you're going to have here A1, A2, and A3. And if you do that, you're going to end up with a 2 by 1. And this is a 2 by 3. This is a 3 by 1. The two inner columns are equal, and it ends up with a 2 by 1. Let's try part B. So I'm going to let A be A1, A2. There's two columns this time. Times our 4, 7, where A1 is our first column, A2 is our second column. If I multiply these, I'm going to get 4A1 plus 7A2, which is the same as 4 times our first column plus 7 times our second. Let's multiply those so you get 8, 32, and negative 20, plus negative 21, 0, and 14. Add those together, we get a negative 13, a 32, and a negative 6. And it all works because this was a 3 by 2. This is a 2 by 1. So you can see the answer is going to be a 3 by 1. The X, the number of entries in X, has to match the columns of A. There is a shortcut on how to do example 1, part A. If you notice, example 5 is the same exact matrix, but now they're doing it with a shortcut. So what they're doing here is they're looking at this first row with the entries of X. So we're going to take 1 times the 4, plus 2 times the 3, plus negative 1 times 7. Sometimes they call this the dot product of the first row of matrix A with the entries of the vector X. And then to get the next one, they just look at the dot product of the second row of matrix A with the entries of column X. So you get 0 times 4, negative 5 times 3 added to negative 5 times 3 added to 3 times 7 If you figure all these out, you get the same answer that we got here. So redoing part B with the shortcut method, I'm going to take my first row and take the dot product of the first row of a matrix A and multiply. So redoing part B, I'm going to, using the shortcut, I'm going to take the dot product of the first row of matrix A with the entries in vector X. And what I'm going to get is 2 times 4 plus -3 times 7. And that's going to be 8 plus -21, which is our -13 that we got here. And you can see it's really the same thing. Here's my 4 times 2 is 8. 7 times -3 is -21, and just do it all in one matrix. So the next column would be 8 times 4 plus 0 times 7, which is just 32. And finally, the last one would be -20 plus 14, which is the -6. Same answer as what we got here above. So let's look at example 4 in the book. It's asked to compute A times X, where A is this 3 by 3 matrix and X is an R3. This does make sense because A is a 3 by 3, X is a 3 by 1, so the resulting is going to be a 3 by 1. So let's go ahead and do this. A times X is the matrix 2, -1, 6, 3, 5, -2, and 4, -3, 8 times my X. I'm just going to do this using the shortcut. So I'm going to look at my first row and second column, take the dot product of the first row of matrix A with the entries in vector X. The second one I'll show. Here it is. I'm going to take the dot product of the second row of matrix A with the entries in vector X. So I get -x1 plus 5x2 minus 3x3. And finally, the last row here would be 6x1 minus 2x2 plus 8x3. And that would be the answer. So what a matrix equation is if I set this equal to some 3 by 1, because the resulting matrix needs to be a 3 by 1. You can see that there. So I'll set it to some B1, B2, B3, which sometimes we call vector B. That is your matrix equation, which brings us to theorem 3. Here it is. If A is an n by n matrix again, with columns A1 through AN, just like before, and B is an Rm, we'll see why in a minute, this is the matrix equation. AX equals B. And we're going to see that this is directly related to our vector equation. x1a1 plus x2a2 plus xn a linear combination of our column vectors of A, a linear combination of A1, vectors A1 through AN, with x1, x2, ... all the way to xn to be the weights, and equaling the B that we had equal over here, because the left sides we saw are the same from above. And our vector equation is going to have the same solution set as our matrix equation, which in turn has the same solution set as the system of linear equations whose augmented matrix was our same column vectors equaling that same b. And again, I like to put a line right there. So these are the three ways that we're going to represent our system of linear equations. So first we did it with an augmented matrix. Then we did it with a vector equation. And now we're going to represent it by a matrix equation. And there's going to be benefits to both, all three, you will see. But first, let's look at another example. Let's just practice writing the system as a matrix equation, writing the following system, a vector equation, and an augmented matrix. Let's start with the augmented matrix. Since we have three variables, we're going to have three columns here, A1, A2, A3, and B. So let's let A1 be 1, 0, A2 be 3, 4, A3 is -2, -3, and B is 5, 7. So our augmented matrix, we know, is A1, A2, A3, and B. So 1, 0, 3, 4, -2, -3, and 5, 7. We did that in our first couple of sections. Next, let's look at our matrix equation. The AX equals B. Let's let A be A1, A2, and A3. And X be X1, X2, X3. You can see that X is an R3, B is an R2, and AI is also an R2 for I going from 1 to 3. So A1, A2, and A3 are all an R2. So A has to be a 2 by 3 matrix. So let's look at that. AX. So again, each AI has two entries right there. Here's where A1, you can see each one of them has two entries. So it has two rows. And there's three columns, since there's three column vectors, times the X. The X has to have, there's where X is in R3, it has to have three entries. It's a 3 by 1 since it's a column vector, and it's going to equal B, and B we see is a 2 by 1, which does make sense. So all the dimensions match up. So we can go ahead and write down our matrix. We can write down AX equals B. So here's AX equals B, and that is the columns of A. Let me make that a little smaller so we can see it. A1, A2, and A3. Leave the X like that, and the B is 5, 7. So this is our matrix equation. Writing, let's make this smaller so we can see the beginning. We wrote the system as a matrix equation. So let's do a vector equation next. Here's our vector equation. Again, that's the theorem up there. And we're going to write that with our A1s, A2s, and A3s, and B. Doing that, here's what you get. A1, A2, A3, and B. You could do this just by multiplying this out by the definition of multiplication. X1 times the first vector, X2 times the second vector, and X3 times the third. Which you can see right here, multiplying that out. And if we do a check, multiply that through the X1 plus 3X2 minus 2X3 equals 5, and then the second row there is 4X2 minus 3X3 equals 7, we get our original system. We've done a full circle. So again, let's make that small again so we can see that was indeed our system of equations. So that is the whole problem for that example. And again, these are the three ways we're going to rewrite our system of equations, or we're going to notate our system of equations. We've seen the benefits of an augmented matrix, the benefits of a vector equation. So in our next video, we're going to look at the benefits of why you would write your system of equations as a matrix equation.